So as we start looking at some applications of all of this, I want to start with a few applications that deal with right triangle trig, and then also today we're going to look at one that deals with what's known as harmonic motion, okay? But we're going to see how we can look at what we've already learned about the graphs of these to help us then figure out things about what's known as harmonic motion. We'll define that a little bit later, okay? Before we actually do some problems here though, I want to highlight two terms, okay? These are terms that you may or may not have ever heard of before, but we have what's known as an angle of elevation and an angle of depression, okay? Now, these angles are angles in situations where one thing is above or below the other, okay? So we might be on the ground looking at something, or we might be here on the second floor looking out at the football field below us, okay? And really these two angles are talking about the same angle, as we'll see in a moment. It's just a matter of your perspective, okay? So here, if we have the person who's observing at the bottom looking up at something, the angle that they have to look up is called the angle of elevation, okay? And as you can see here, it's always measured from the horizontal, okay? It's always measured from the perfect horizontal. And as you can tell, if we were then to draw a line straight down from our object, we can very easily get a right triangle, okay? So if we're at the bottom looking up at something, it's an angle of elevation that we have to tilt our head or turn our eyes up to see it, okay? And there are different tools that, like if you were actually doing this, you could use like a surveyor's tool to look up at something to determine elevations. You know, different navigating tools have, I forget what they're called, but they also have ways to measure the angle that you would have to look up from a horizontal to see what that angle would be. Yeah, Jared?
A few weeks ago for our physics class, we had like an extra credit project, and we had to like measure the maximum height of the fountain in the lake.
Mm-hmm.
Kind of like using this right triangle stuff.
Yeah?
Yeah,
Cool.
it's really the same stuff.
Cool. Good. Now, on the other hand, if you're at the top looking down at something, that's what's known as the angle of depression, okay? And as I've said, this is kind of a matter of your perspective, okay? Let's take the case where here we have a horizontal, you're standing down here, okay? And there's a plane up here, okay? Okay, here's our plane. That's halfway decent for me, okay? So there's our plane, and the pilot is up here, and they're looking down at you, okay? So, as you're looking up at him, you have what's known as, if there's a horizontal, an angle of elevation. As he looks down at you, he would have the angle of depression.
Those are equal, right?
They are equal. Why are they equal?
Because they're, what's it called? They're corresponding angles?
You're in the right context.
Something like that.
Something like that, because the horizontals are parallel to each other, okay? The horizontals are parallel, so we have these parallel lines being cut by our line of sight could be called our transversal. And do you remember what those two angles would be called? They're between the parallel lines, but on opposite sides of the transversal.
Not corresponding.
No. Alternate
Alternate interior.
interior angles, okay? Now, you don't need to remember the terms from geometry, you just need to remember that those are congruent. And here's why. You might be asked to find how high the plane is off the ground, but you're given an angle of depression, and then you're like, oh, well, that's not in my triangle, you know? Well, use the alternate interior angle, and you can figure out you do have an angle in the triangle, okay? So, at this point, I want you to practice using this, and this is where you're going to get together with a partner here. So I want you to move your desks together. You can be in a group of 2 or 3, and I want you to work through these, keeping in mind SOHCAHTOA, your right triangle stuff. Sine is opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent is opposite over adjacent, all right? So take a few minutes. I'm going to give you about 4 or 5 minutes here to try this one, and then we'll take a look at it, and then we'll do a second one. All right, so we can see what Ryan did here. We have the sine of 72 is going to be our A over 110, okay? So we multiply both sides by 110, so 110 times the sine of 72 does give us 104.6 feet.
Oh yeah,
Okay? Any questions on that one?
I get the math. Why is it A? Because that's like on the opposite side, isn't
It is on the opposite side, but it's, think about it, we're just dealing like with a rectangle, basically. If we were to draw it like this,
it?
so opposite sides of a rectangle would be congruent. So, okay. All right, so some of you have started this one already, but go ahead and get going with this. Notice this part S is only from here to here. That's what we're looking for. Okay, but we don't know how tall the building is yet, so we can find this out. All right? All right, so Han shared with us her work. Let's take a look at it. Okay. This whole thing here is A plus S. And we had to use tangent because this is the opposite side and this 200 that we were given is the adjacent.
Easy.
Guys, this is how we measure things that we can't physically get to measure, all right? For example, what if instead of a building and a smokestack, this were a river that we had to build a bridge across of? If we pick a point across there and get to a point straight across from it, and then we measure over, we can measure to like 2 different points and we can figure out distances, okay? So, you know, you can use this anytime it's hard to physically measure something. You can use trig with a couple of different angles to help you measure things. So, in this case, we wanted to measure this smokestack on the top of the building without having to climb up there. So we measured away from the building 200 and then measured 2 different angles. Okay, so tangent of 53 is the whole thing over 200. So the whole thing, A plus S, ended up being 265. And then we used the smaller triangle that just had A in it and a 35-degree angle. And tangent of 35 was A over 200. So we figured out that the building was 140 feet tall. So if we subtract, we got that the smokestack itself was approximately 125.4 or 0.367 feet tall. Okay? Any questions about that one? All right, good, good. Now, this is kind of an interesting application, all right? We have what's known as simple harmonic motion, okay? Simple harmonic motion. What this is designed to do, guys, is to model a situation where we have something and we always just put that thing at 0, okay? and we have something that's moving up and down and up and down and up and down and up and down around that zero. That's simple harmonic motion. These could be, the height of a buoy floating on the ocean when the waves are coming by, and it's just kind of going at a consistent up and down and up and down. All right, so we would think of the middle of it as being zero, and then you can figure out its amplitude and period and whatnot. Okay? You'll notice here the formula, though, instead of a y coordinate, we think of d, because d is the distance that we've traveled up or down. You could also call it displacement. All right? It would naturally rest along that zero, but some force is causing it to go up and down and up and down and up and down.
Isn't that kind of like the amplitude in a way?
It is the amplitude, and that's why a here, a times the sine of this symbol here is an omega. A times the sine of omega t, or if you want, you can use cosine. All right? Now the nice thing about this, guys, is look, there's no horizontal shift and there's no vertical shift. All we're looking at is a change in the amplitude and period. This is like what we would use for music waves, sound waves. There is no start or finish. We just, when we start playing the sound, that's zero, and silent, or the whatever the midline is, we just treat as our zero, and then we look at its frequency and that sort of thing. Okay. Now the only real difference here in the formula is that instead of using a b, we use this symbol omega, and that's just a carryover from physics. Okay. But there's a couple of things here that we can see, and one of these, you'll notice since we have omega instead of b, the period is 2 pi divided by omega. All right? But then we have this other concept here, the frequency. The frequency is, rather than looking at how far it takes to repeat, the frequency is how many times does it repeat per unit of time. This is what hertz are. Hertz are cycles per second. Okay, so if our time was measured in seconds here, we would have the number of periods or cycles per second. That's hertz. That's your frequency. Okay, the higher the frequency in music, the higher the pitch. All right, so an A440 is the note A, but if I do an A220, the frequency is much less often, so it gets to be a much lower note, a note that's exactly 1 octave lower. If I do an A that's 880, the frequency has now doubled, so I have still a note that we call an A, but now it's an octave higher. Okay, that's how music works, and that's how we're able to actually make musical notes with, computers and stuff. We are just plugging in different frequencies in. Yes.
Tricks, is it possible to make just with trigonometric functions waves that vary like this, small and large, and small, large?
That's harmonic motion. It's not simple harmonic motion. There's ones like if you pull a spring, initially it starts bouncing and then it slows down until it's just still again. Okay? It's possible, but it isn't just a simple sine of omega t. There's other parts to the formula too. So it's a little bit different. We're not going to mess with those. There are some in your book. We just don't take the time to look at them. Okay, so if you want to look at the chapter in this section, they do go on and kind of expand on this a little more, if you're interested in that. Okay. But here, notice what we can do. We can use our transformations. To figure out some different things here, okay? So, think with me here. what would the maximum displacement be if our distance equaled 6 times the cosine of 3 pi over 4 times t?
4.
12, 30.
The maximum displacement, if we're starting at 0, what's our amplitude here?
18 pi. Cosine 18 pi.
Hang on. Our amplitude is 6, right? So amplitude is 6. So where is cosine going to start?
Up at 12.
It's going to start up at 6 and it's going to go down to -6, right?
Yeah.
So this is what this is going to look like. The next question is, where does it end? What's our period?
3 pi over 4.
That's omega. What is it?
The period?
I was gonna say 2 pi over times.
8 over 3.
Oh.
Over 3 pi, but I don't.
No, that's right. That's right. 2 pi over omega, which is 3 pi over 4, which is 2 pi, as Rachel said, 2 pi times 4 over 3 pi. So the pi's cancel, and we have 8/3. So every 8/3 of a second, if we're talking about seconds in this case, this thing is going to repeat. So that's at 8/3, that's our period.
Why does 4 over 3 pi equal 8 over 3?
It doesn't. 2 pi times 4 over 3 pi equals 8 over 3. Okay? So let's think about this. What's our maximum displacement? 6.
Wait, Mr. Why do the pi's cancel out if you multiply? Because you divide it, never mind. Yeah.
Wouldn't your maximum displacement be 12? Because if you're in the top and once you go to the bottom.
Well, remember, displacement is your y coordinate in this case. In harmonic motion, d is your displacement. So the max value of d here is at 6. We're not talking about the maximum difference between the highest and lowest points. We're talking about the maximum displacement from
The
0. From that would be like our position at rest.
What if the top coordinate would be 5 and the bottom would be like -7, so would it be 7 then?
Actually, no. When we're talking about harmonic motion, we never shift the graph up or down. So it will always be up 6 and down 6, or up the amplitude and down the amplitude.
Okay, so it couldn't be like 5 and -7 or
No,
anything?
no.
Okay.
Not with simple harmonic motion. We always center it on the x-axis. Okay. What's the frequency?
3 over 8.
Yeah, it's 3 over 8. Notice the frequency is just the reciprocal of the period. Okay? So it would be 3 over 8. Okay? And then the value of d when t equals 4. We could actually do this without a calculator.
36.
Alright? D is 6 times the cosine of 3 pi over 4 times t. T is 4. What's the cosine of 3 pi?
2. No. Minus 1.
Number when you use.
What'd you say, Davi?
Minus 1.
It's -1, because we've gone around a full circle and then we're back over to pi again. That's at -1. So the displacement would be -6. Okay? Then the least positive value for t for which d equals 0. So in other words, what's the x-coordinate right there?
4, whatever half.
What?
Whatever half of that. 4/3.
Okay, so, 4/3 is where we would be at the bottom, right? Halfway through the period.
Oh, no.
So then this would be at
2/3.
at 2/3. Okay? if you divide your period into quarters, 2/3, 4/3, 6/3, 8/3, okay? So 2/3 is the t that would give us d equals 0, okay? So kind of a cool application there. With any kind of thing that's moving just up and down around something, we can figure out where it's going to be. This, guys, is what your computer in your car has to figure out in order to fire the spark plugs correctly. You have pistons in your car, in the engine, the cylinders in your car that move up and down, okay? They move up and down. At the bottom is a little injector where fuel comes in, and the spark plug is down here, okay? And when this is right at the bottom, the spark plug creates a spark and catches that gasoline on fire, causing an explosion that pushes the piston back up. That's why it's called an internal combustion engine. The spark is exploding. If your timing is off, then some of that explosion creates this air in here just to compress, and you lose power. It won't push, it'll still push the piston up, but not with as much power, and you lose power in your engine. So that's why the timing is critical in your engine. All right? So that's one application of this kind of harmonic motion. All right? All right, cool stuff. All right, so listen, start preparing for our test next week. Come with questions. We'll look at modeling on Monday and review on Wednesday, and we'll have your test. All right? Have a great day.